Today we are going to look at how we express the position vector using the ij notation. Now the position vector is simply a vector that shows the position of a particle relative to its origin. This is the origin, 0, 0. So if we're having a particle p at that point, it means that the position vector or the position of this particle p from the origin means that you're going to move certain steps in the x direction and then certain steps in the y direction to be able to reach point P. And in this case, when we are using the ij notation, the I in this case denotes for x, how many steps you have to make in the x direction, then the j stands for the y. So these are meaning that if this was let's say if from O to A, if this was, let's say, 5 units from here to there, and then this part where this was 5, and from here to here, let's say it was 8, it would mean that the position vector of P, first of all, the coordinates of P will be, from the origin it will be 5, comma, and then when you go along the y direction it will be 5, 8. And if it is 5, 8, it simply means that if we are to use the ij notation to represent the position vector of P, in this case which will be OP, so meaning that the position vector of OP will be 5 in the x direction, so the x direction is denoted by I, then plus 8, it is positive 8, and that is in the j direction. The j direction in this case will be in the x direction, and so it means that the position vector of P, which is OP, is 5i plus 8j, and that is how we generally express position vectors using the ij notation. Now, with this ij notation in general terms, if we want to find the magnitude of this vector, this is O to P. So it means the magnitude simply means that we look at it this way. If this forms something called like a right angle triangle, as you can all see right here, so to get the magnitude of R, we use Pythagoras theorem. Now we know that Pythagoras theorem for a right angle triangle is that this line squared plus that line squared gives us this line squared, and in this case we are having this side which is A, denoted by A, so it's going to be A squared plus that line which is B squared, because from here to here it is B, so which is B squared, that's going to be C squared, and in the case C squared is R squared. So when we make R the subject of the formula, it's going to end up being under the square root of A squared plus B squared. So now R, the magnitude of R, though the magnitude of this vector OP is denoted by A squared plus B squared. That is in general terms. Now when it comes to find the direction of this vector, the direction of this vector simply means that we are being tasked to find the angle between the vector and the horizontal. And here we are simply going to use one of our trigonometrical identities. To get the value of theta, we can use the tangent of that angle. We know that the tangent of that angle theta is going to be equal to the opposite, and in this case this is the right angle triangle we're looking at. So the opposite in this case is B, so it's going to be B over adjacent. The adjacent in this case, it is A. So when we make theta the subject of the formula, theta is going to be the inverse of tan inverse of B over A. So when we are faced with a vector like this, in ij notation, P of AI plus Bj, if we want to find the magnitude, this is the general expression, and if we want to find the direction, it is that. And that is exactly how we state them, that the magnitude is going to be this and the direction will be exactly like that. Now let's look at the velocity vector using the ij notation. Now looking at this velocity vector, for example, here we are having a particle still. Let's say this is our particle here, and we are calling that particle P. Now we need to find the velocity of this particle. The velocity vector of this particle is given that the velocity of this vector is ci plus dj. Still I is denoting the x direction and j denoting the y direction. Now this is the velocity vector of this. Now if we want to find the position vector of r after a certain time t, we do not know the time. Let's say this thing, originally it was at this point r. Now it starts moving at that velocity. So it means that if we want to denote the position vector of this value of p after a certain time t, it would mean that still we are going to first add the position vector of this value of p from the origin. Then after we get it and add on the distance it has traveled. This is the particle p. It is moving with a certain velocity. So meaning that if it is to move, it is going to move a certain distance. Let's call that distance. Let's call that distance s. So it means that if we want to find how long this particle p has moved at this velocity, we know that distance is given by speed times time. So if I want to know the distance traveled by this particle p, I'm simply going to get the speed, which in this case the speed is the value of v times time. Is going to give us the distance. So meaning that if I want to find the particle p, how much it has moved using this velocity, I'm simply going to find the velocity times time, and I'll get the distance moved. Now since here we are dealing, our velocity is in terms of ci plus dj, it is a velocity vector. It means that if I want to find the vector, how much this particle p has moved, I'm simply going to get the velocity vector, multiply that by time. So meaning that after it has moved at that speed, if I want to know now how much, if I want to know its position vector after a certain time t, it would mean that I have to add this distance it has moved plus its initial position vector. So this is going to bring us to this, that if I want to find the position vector of a particle after a certain time t, the position vector will be given by the new position vector will be equal to the initial position vector of this particle plus the vector that is representing the time, how much it has moved. Let's illustrate this using an example. We have a particle, it has an initial position vector of this, and if the particle moves with a constant velocity of that, find the position vector of p after a certain time t. So now we want to find the new position vector after the thing has moved for some time. So we'll work it out this way. Initially this particle had an initial position vector. Let's say this is the particle p. It had an initial position vector of 3i plus 2j plus 4k. And then it moves with a certain velocity. Now this is initial position vector of p. Then it is moving with a velocity of 5i plus j minus 3k. So for me to be able to find its new position vector after it has moved would mean that it's going to be, let's denote it by r. The new position vector r after a certain time t is going to be given by the initial position vector, the place where it was initially, which was 3i plus 2j plus 4k. And then this is the position vector from the origin initially. Then plus, we are supposed to add that extra distance that it moved. So that we add the distance it moves with this velocity plus the distance it is from the origin for us to be able to get its new position vector from the origin. So it means that we are going to first add the distance from the origin plus the new distance it travels. The new distance it travels is going to be speed times time. The speed we are having here, or which is our velocity, is that one. So it means that it's going to be the speed times the time. And the time here we do not know, because the question is telling us after a certain time t. So it's going to be the time times the velocity it moves, or the speed it moves, which is 5i plus j minus 3k. So this is the general. Now of course this continues. this becomes 3i plus 2j plus 4k plus, now of course we open brackets here, this is t times 5, which is 5ti plus t times j is tj minus 3 times, it is minus 3 tj. Of course now we are going to group the i's alone, the j's alone, and then the k's alone, and in this case it's going to become, this is 3 plus 5t, so this is going to be 3 plus 5t, these are the i's, then plus, this is 2j and this is t, so it is 2 plus tj, so it is 2 plus t, and this is in j, then also plus 4 minus 3, 4 minus 3, that is k, this is k, so it's 4 minus 3k, 4 minus 3t, this is in k, and definitely this is now the general expression in ij notation for the position vector of this at any time t. We could as well express this in another way, in the column form. For example, if this, it's another way of writing it. If we said r of t is going to be equal to 3i plus 2j plus 4k can be written in form of 3, 2, and 4. This is vectors in column form. Plus, this is t outside into 5, 1, negative 3. 5, 1, negative 3. And still this would lead us to 3 plus 5t, which 2 plus t, which this is 2 plus t, then 4 plus negative 3t, so it is 4 minus 3t. And of course this will still lead us to this is I, this is J, this is K. So still RT is going to be equal to 3 plus 5TI. This is the I direction, this is J, this is the K. So it would still be 3 plus 5TI plus 2 plus TJ plus 4 minus 3K. 3TK. So you still find yourself that you're ending up with the same expression as here. So that is the position vector of P. This is the expression for the position vector of P after a certain time t. Now let's go ahead and do part B. Now part B is asking us to find the position vector of P after 3 seconds. So if it is after 3 seconds, it means that since we have the expression for the position vector after a certain time t, now here they are telling us that the time is 3 seconds. It means we are simply going to substitute for the value of t. We are going to put there 3 seconds and we get the position vector after 3 seconds. So in this case, the position vector after 3 seconds is going to be position vector after 3 seconds, which is r after 3 seconds, is going to be equal to, still from our earlier expression, it's going to be 3 plus 5t. Now our value of t is 3, so 5 side 3. All this is I plus 2 plus, that is 3. Our value of t is 3, j plus 4 minus 3, so it is 4 minus 3t. The value of t in this case is 3, that is k. So that's going to be 3 plus 15. So the position vector after 3, is going to be this. This is all in meters. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.